Okay, so let's watch this. I'll just type here like, what do you know about me? So I'm in a kind of brand new browser session and fresh start, and I'm asking this agent what it knows about me. And here it is giving the responses. Okay, your name is Shweta, you like coffee. That's what I have so far. I'd love to know more about you though. What else would you like me to remember? For instance, what do you do work for today? So this is kind of that information is coming from a SQLite database, not chat history, not a start prompt, a database. I closed the browser, restarted the app, and it still knows me. So every AI assistant has the same problem. Close the tab and you are a stranger again. Today we are fixing that permanently. So let's build this. Here is the problem I kept hitting. I had built a chatbot, right, and the thing was smart. It was helpful, but every single conversation started from zero. You tell it your name on Monday, and by Tuesday, it had no idea who you were. For a demo, that's annoying, right? For an actual product, that's a deal breaker for sure. The typical fix everyone reaches for is just dump the whole chart history into the context window, and yeah, that works for a while, but then your history gets long. You are paying for thousands of tokens on every single request, half of it is irrelevant, and eventually you just hit the limit. It's a patch, not a solution. So what we are building instead is a proper two-layer memory architecture. Layer 1 is very normal, the messages in the current conversation, and layer 2 is a persistent store backed by the SQLite, where we extract and save meaningful facts about the user after every single turn. Things like their name, their job, what they are building, what they hate, those facts live on disk and survive restarts, deploys, everything. And the retrieval is very smart, so we are not loading every memory every time. We are using semantic search here, turning the user's message into a vector, comparing it against all stored memory vectors and only injecting the relevant ones into the context. So when you ask about coding preferences, you get the Python memory, not the one about your coffee order. The whole thing runs in a 3-node LangGraph pipeline, and the front end is Streamlit with a live memory panel, so you can literally watch facts get stored in real time. So here is what we are covering today: embedder, memory store, the prompts, the agent graph, and the UI. We'll go file by file for everything, and I'll show you every function that matters. So let's go first walk through this architecture diagram first. Okay, so let me walk you through how this actually hangs together, because once you see the shape of it, the code is going to make a lot more sense. So data comes in at the top, that's the Streamlit UI in app.py. The user types a message, and we have got this split panel layout: 70% chat on the left and 30% live memory records on the right. Then that message drops into our LangGraph agent in agent.graph.py, and this is where it gets interesting. The graph has 3 nodes, and they run in strict order every single time. So here we are coming as the node 1, that is the recall memories. Before the LLM ever sees the user's message, this node goes to the memory store, embeds the user's query, and does a semantic similarity search against every stored memory. It pulls back the top 5 most relevant facts and injects them into the state. Now let's come to the node 2, which is our run agent. This is your actual Claude powered chatbot. It gets the system prompt with those recalled memories backed in. It gets the chat history, it gets the new messages, and it responds. But it responds like someone who actually knows you. Now coming to the node 3 is extract and save. So after the response is generated, we make a second cheaper LLM call to pull out any new facts from this conversation turn. Did the user mention their job, their location, a preference? Those get written to SQLite immediately. Now down to the bottom, we have got two supporting files. Those are memory store.py and embedded.py. So memory store.py is the only file that touches the database. I was very deliberate about that. And embedded.py is a singleton wrapper around a local sentence transformer model that handles all the vector conversation. So I tried building this as one big file first. It was a nightmare to debug because when something went wrong, I had no idea which stage failed. The separation into nodes makes that obvious. So each node's output is inspectable. Each file has one job. Alright, let's set this up and then get into the code. Let's real quick on the stack. I want to explain the choices, not just the names. So Claude via LangChain Anthropic for the LLM. So could I use GPT-4o? Absolutely yes. I am using Claude because it's unusually good at structured extraction tasks, and our memory extraction step is basically asking for it to output one fact per line with a very specific format. So Claude follows that reliably. LangGraph for orchestration. This is not LangChain's generic agent loop. It's an explicit state machine where I define exactly what runs in what order. For a memory pipeline where sequencing is everything, that explicitness is the point. And sentence transformers for embeddings I have used here, and this one I feel strongly about because it runs completely locally, no API call, no latency, no cost. The all mini LM L6v2 model is 80 MB, loads in under a second after the first time, and produces genuinely good semantic embeddings. The alternative is paying OpenAI for embeddings on every single memory operation. No thanks. I'll just go with this one. So SQLite utils instead of row SQLite 3 because it lets me do dbmemories.insert row dict instead of handwriting SQL strings, and NumPy for the cosine similarity math. 2 lines of code, no vector database needed at this scale for sure. So let's get set this up. So we'll first do one make directory with the agent name. Suppose I have given it persistent memory agent, and then you have to go to that cd persistent memory agent. After that, I have been creating one virtual environment here, vnv ng source vnv /vn and activate. So this will be activated within some time. Then after that, create your requirement.txt, which I have already done for myself. So let's understand why each library is here. So Anthropic plus LangChain Anthropic, these connect to Claude, and LangChain Anthropic gives us the chat Anthropic wrapper, so LangGraph can work with it natively. And LangGraph, this is the orchestration framework. Think of it as like a state machine that defines the flow, recall, respond, and write. And LangChain core provides the message types: system message, human message, AI message, like those. These are the building blocks for talking to any LLM. And sentence transformers. This is how we generate vector embeddings locally. No API call needed for this part. Streamlit. This is the UI layer. NumPy, used for the cosine similarity math when we do semantic search. SQLite utils. It is a nice Python wrapper, our SQLite for inserting and querying rows. python.env, that is the loads your .env file, so the API key doesn't get hard coded. TikToken, it is an open source tokenization library mainly used for converting text into tokens, and it means counting tokens in prompts or responses. It will also manage the model context limits or whenever you are estimating your API uses or cost. We have to install all of this by doing the pip install -r requirements.txt. You can just give it inside the directory, and then after that it will create all of the install all of the libraries to your application. But there also you will get one fair warning about the sentence transformers, because it will pull in pyters, so that's a big install. So if you will give it a minute, once that is done, you can just go proceed with your stuff. And you have to grab your Anthropic API key from console.anthropic.com, and it starts with something like sknt ... so, and drop it in a .env file like this, how I have given here, and immediately add .env to your .git ignore because it is non-negotiable. Okay, so let's walk through the code once. So first we'll go with this init_db.py. so as you are seeing here, right, init_db function, so this is your database schema setup file. It runs once to initialize the SQLite database by connecting it. So here we are creating two tables. So two tables are created. One is memories. This is the core table. Each row stores user ID, embedding, content, importance score. So user ID, so memories are isolated per user. User A's memory don't leak to user B. Content is the actual fact as a string, that is user's name is Shweta. Embedding, the vector representation of that fact stored as JSON text. So SQLite doesn't have a native vector type, so that's why we serialized it. Importance score, this is a schema hint for future use. Right now it's not heavily used, but you could filter by it. Sessions tracks the user sessions, not actively used in the current app flow, but it's there for session level analytics or future features. And why indexes we have given here also, because the IDX memories user ID index ensures that when you run where user ID equal to, SQLite does not scan the entire table. It jumps directly to the right rows, and this matters at scale. So that's how we have been configured this DB here, and then after that connecting to the SQLite, we are calling it from here. So going to the next coding, that is the embeddings.py and embedded.py. So these two files do the same job. Embeddings.py is used in agent.py. It's like the more advanced version, and the embedded.py is used in agent_graph.py, that is the simpler version. So let's look at the pattern here. That is the Python_model equal to none, that is the underscore model what you are seeing here. So it is first getting the embedding here. So this is this get embedding what you are seeing here. This is a lazy singleton pattern. The model is only loaded the first time you call the get_embedding. After that it's cached in the underscore model global variable. Why? Because loading a sentence transformer model takes a few seconds. You don't want that cost on every single function call, only once per app. So lifetime, all mini LM L6 V2 is the model name we have been used here. It's a small fast model from Hugging Face that produces 384 dimensional embeddings. It runs locally, so no API call, no uses. And then after that it is normalized the embeddings equal to true, means the output vectors have unit length, that is equal to magnitude equal to 1. This is critical because it makes the dot product equivalent to cosine similarity, and cosine similarity is what we use to find semantically similar memories. And if we will go here into the memory underscore store.py, this is the core storage and retrieval engine. So it's a class that wraps the SQLite database. So if you are seeing here Python class memory store, and here we have been given this init function and init table function, all of this, and checking the same thread here equal to false. So this is the important for Streamlit. Streamlit runs in a very multi-threaded environment, and by default SQLite raises an error if you access a connection from a different thread than it was created in. So this flag disables that restriction. Now the two most important methods are write memory. So write memory, as you are seeing here, this embedding, get embedding underscore JSON. So when a fact is saved, it gets embedded immediately at write time. This is a deliberate design choice. You pay the embedding cost once at write, not repeatedly at read. That is the function write memory. And the next function is the recall memories. So recall memories, this is your semantic search. So here is what's happening step by step. So it will fetch all the memories for this user ID from SQLite, then embed all the incoming user query with the same model. For each stored memory, deserialize its embedding and compute np dot the dot product against the query embedding. Because vectors are normalized, this equals cosine similarity, sort by the score descending, and return the top k most relevant facts. So this is essentially a mini vector database implemented from scratch using NumPy. It works great for moderate memory counts and hundreds to thousands of facts at millions. So you would want something like Chroma or PG vector, like that. So coming to the next, we'll see the agent prompts.py, which is giving our agent prompt. So two prompts live here. Agent system prompt, injected as the system message on every LLM call in Python, and here we are giving agent system prompt like you are a persistent personal assistant with genuine long-term memory, like that. And recalled memories about this user is memory underscore block. So the memory underscore block is a format string placeholder. At runtime, the recalled memories are injected here. This is how the LLM knows what it knows about the user. It reads them right in the system prompt. This is called in-context memory injection. The model doesn't have true state, but we simulate memory by passing the facts into the context window. And memory extraction prompt we have been giving here. This is sent to the LLM after each conversation turn in Python. So here we have been given the prompt like your job is to extract key factual claims about the user message plus assistant response, and the outputs in a bulleted point we have been given here. And notice the instructions are very specific, only facts about the user, not about the assistants, no vague conservation. So each bullet should be a standalone sentence. This is careful prompt engineering to keep memory quality high. And after that we will be going to the agent_graph.py. So this is the very simple version, and this is the main LangGraph agent. So let's understand the structure first. What is the state definition here? As it is going the agent state, it is taking user ID, user message, chat history, recalled memories, assistant response. So this is a typed dictionary. It defines the shape of data that flows through the entire LangGraph pipeline. Every node receives this dictionary and returns an updated version. Think of it as a carrier bag that all nodes read from and write to. And coming to that, this is our node 1, which I showed in the architectural diagram, that this is the memory underscore recall node. So it is taking the current message, calls the recall memories on the memory store, and adds the result to the state. So the state spread preserves all other fields, and we are only adding recalled memories here. And this is our second node, which is the LLM respond node. So LLM respond node, here we are giving also the system prompt, and that is coming from the agent system prompt which we have written there. So this node formats the retrieved memories into the system prompt, reconstructs the full conversation history as LangChain message objects, calls the Claude, and returns the response. So as you can see here, how the LLM itself never touches the database. The only thing it sees is the formatting system prompt with the injected memories. So clean separation of like any concerns. And then this is the third node, which is the memory write node. So after every response we immediately extract some facts. The LLM is called a second time. This is the extraction LLM call. It reads the exchange extraction bullet points and saves each fact to SQLite. So why a separate LLM call instead of asking the response LLM to also extract facts? So separation of concerns. The response LLM is focused on being helpful, and the extraction LLM is focused on being a structured parser. Mixing them degrades both. So if you will see here, we are doing this graph varying inside this build graph function here. As you can see here, this is the LangGraph DAG, directed as cyclic graph. So the edges define the execution order. As you can see, this is the start, and then it is the memory recall it is going, and after that LLM respond, and after that it is going to memory write, and this is the end. So graph.compile here validates the graph and returns an executable object. And after that, every time you call this dot invoke, it returns the full pipeline from start to end. Now coming to the next one, this is the agent.py, which is the very advanced version, and it is a more complex version of the same pattern. So the key differences, I'll say, like, it uses a richer agent state that also tracks current input and new memory to write, and also it uses a separate LLM and extraction LLM instances, that is potentially with different models or parameters. Extract memorable fact does JSON parsing on the LLM's extraction output, filtering by an importance score thresholds, and it embeds at the right time, because when it is doing this embedding equal to encode like fact, so at that time it is passed explicitly to store write memory. So think of agent_graph.py as the cleaner, simpler version that's actually wired to the UI, and agent.py is an experimental iteration with more sophisticated memory filtering, I'll say. And here also we are taking the system prompt from the previous prompt.py file, and after that we are calling from here. Don't worry, I'll just paste all of these codes, you can access it, don't worry. So coming to the next part, this is our final part, that is the app.py, which is the Streamlit front end. So as you can see here, @st.cache resource, so that is critical here because Streamlit reruns the entire script on every interaction. Without this, decorator, build, graph and memory store function would be called fresh on every messages, and reinitializing the LangGraph graph and reopening the database connection every single time, it would be like really big hassle, and we can't proceed on our we can't achieve our goal of persistent memory agent. So with @st.cache resource, they are created once and reused for the lifetime of the session, and whatever user id we are handling with this, because we are keeping all the session according to the user id. So when the user changes their id in the sidebar, the chat history is cleared. This ensures a clean context switch. The SQLite memories for each user remain intact, and only the in-memory chat session resets here. So it is handling according to the user id, and when the user changes their id in the sidebar, the chat history is cleared. So this ensures a clean context switch. The SQLite memories for each user remain intact, only the in-memory chat session resets here, and you can see it is giving the prompt and it is going with the chat container, and according to that it's keeping append the session history as well here. And if there is no live memory store also, it is another one, it is going with all the memories. And if you have not done any memories and you are the first time user, then it will tell you okay, no memory stored yet, chat with the assistant to build up the memories for you. And when you are using the st.session_state is the in-memory conversation context for the current session. The recalled memories from SQLite is the long-term cross-session memory, and these are the two distinct memory layers. So the right column is live memory score when you are a first-time user, and it will show you what you have written there. And this is the sidebar panel, shows what's actually stored in SQLite in real time. It's a great way to demonstrate to viewers that the memory is genuinely persistent, not just maintained in session state. So as you can see here, the memory is genuinely persisted, not just maintained in session state. So let me bring it all together. Here is what happens to every single message. So this is our UI, the persistent memory agent, which is the Streamlit app we have deployed here. So when you are a user is typing a message here, something here, and app.py calls the graph.invoke method with the current state, and it is going to the node 1 memory_recall. The message is being embedded locally using the sentence transformer, and dot product similarity is computed against all memories in SQLite for this user. And after that it is going to this node 2, which is the LLM response, and it is retrieving the memories that are formatted into the system prompt, and the full conversation history plus new messages is sent to Claude, and the response comes back again. And after that node 3, the memory writes, the user message plus assistant response are sent to Claude again with the extraction prompt, and facts are passed with and saved to SQLite, each with its own embedding. And after that app.py updates the st.session_state.history and re-enters the chat. And the next session, even after a full restart, begins at node 1 with a fresh recall from SQLite. So the model has never seen this user before in this session, but the memories bring it up to speed it instantly. So this is the complete code base. As you can see here, all the files and every functions are separated and doing exactly one thing. So let's run it, and if you will go it here, I have already made it live here. So if this is the user id user 001, and for me it is giving like that, and if I am giving user 002, something like that, and I'm starting a new conversation, and if I'm asking, okay, what do you know about me, now it's thinking, and watch the memory panel as well. See, it is telling I am a new user, so it doesn't know me, and it is telling I don't have any memories about you yet. This is our first time chatting, so I am starting fresh. But same when I'll do with user 001. That was what I told him before. So I'm again, what do you know about me? Oh, that's clean. You see that, right? To memory just dropped in and the agent responded. So extract and save ran. Claude pulled out two distinct facts and they're now sitting in SQLite with timestamps. So that's the pipeline working exactly as designed. Okay, so there it is. User is building a SaaS product and user dislikes ORMs. You can give everything whatever you want, and till now it only knows my name because I have not given anything. If I don't like coffee, also if it will know, now it will tell me later also the same thing. Okay, this is Shweta and I don't like coffee. Okay, that's good to know, especially since I am apparently had that wrong in my notes, because previously I said that I like coffee. Okay, so fresh session, look at that memory lane, all four records are still there. That's the SQLite database. The Python process restarted and the session state is completely fresh, but the memories are still on the disk. And this is like a stateful agent, that is persistent memory. So what you have seen there is when I have given user 002 but it didn't know me, that is the user isolation. It doesn't have that memory and it is trying to build the memory and doesn't have the like memories yet. So completely separate context, and you can have 100 users in the same database, each with their own memory namespace, and they never bleed into each other, and change it back to the like default user and it will have the same memory again. So that's the full architecture working end to end. Okay, so what we built today is LangGraph agent with real persistent memory. Two-layer architecture, local semantic search with sentence transformers, SQLite persistent live memory panel in Streamlit from scratch in under an hour. The thing I keep coming back to with this project is how much of the magic is just good architecture. It's not a clever model trick, it's recall before respond, extract after respond, and a database that doesn't care when you restart. Stack those three things and suddenly your agent has a personality that carries forward. So you can do your homework like add memory categories instead of just storing the raw text. Tag each memory as one of the identity, preference, project or context. Then in the memory panel, filter by category. It will take you maybe an evening. It uses skills you already have from this video and the result is genuinely more and more useful. So the code is linked in the description. If this helped you, hit subscribe. I'm putting out builds like this every week and they only get more interesting from here. So see you in the next one. Thanks. Bye bye.